Welcome to Naradar Academy. In this video, we are going to discuss about extension fields. We know field is a set defined with two binary operations. One is called addition, another one is called multiplication. With respect to both the operations, it must be a commutative group, that is abelian group with respect to both addition and multiplication. So in this video, we are going to discuss about extension fields and how to find the splitting field for a given polynomial. Okay, so let f be a field and k is another field and it is called an extension of f if k contains f. That is, f is a subfield of k. Okay, k is a field and f is contained in k. In this case, we called k as an extension for f. Okay, for example, see the field of rational numbers is a subset of R. No, R is the field of real numbers. So we can say R is an extension of Q. In the same way, R is a field and the complex numbers, it is also a field and R is contained in C. So we can say C is an extension of R, right? And in this way also we can say Q can be considered as a subfield of C also. So the C can be considered as an extension for Q, right? So this is called extension, and the degree of k over f is the dimension of k as a vector space over f. See, throughout this video, f denotes a field and k denotes the extension of f, right? So what do you mean by the degree of k over f? See, k is a field, both are fields, no? Now for defining the degree, you treat k as a vector space over the field f. Okay, if k is a vector space over the field f, we know how to find the dimension of a vector space, isn't it? Dimension of a vector space is nothing but the number of elements in its basis, right? So if you consider k as a vector space over the field f, then that dimension of k is called degree of k over f, right? If the degree is finite, it is called finite extension, otherwise it is said to be infinite extension. For example, if you consider the field of complex numbers over the field of real numbers, that is C as an extension of R. If you consider C as a vector space over R, then its dimension is equal to 2, because the set containing 1 comma I is the imaginary part, no, 1 comma I, that will constitute the basis for the vector space C over the field of real numbers. So the basis contains only 2 elements for C. Therefore, the degree of C over R is given to be 2. So this is a finite extension. C is a finite extension of R. Then next one, if we have 3 fields, okay, F, K, L. K is an extension of F and L is an extension of K. Then we can say L is an extension of F also, isn't it? Already we have seen here. R is an extension of Q and C is an extension of R, and we can say C is an extension of Q also. In such a case, how will you define degree of L over F? Then degree of L over F is given by degree of L over K into degree of K over F. So this is the relation. That is, if degree of K over F is M and degree of L over K is N, then degree of L over F is given to be M into N. Then next one is algebraic. So when will you say an element as an algebraic element over the field? See, an element A belong to K is said to be an algebraic element over the field F if there exist elements alpha naught. That is, we have to choose a polynomial in F. Okay, we have to choose a polynomial in F such that this element in K is, this element A in K satisfies the polynomial over F. Then that element said to be what? Algebraic over F. That means F is the smaller field, no? Over the smaller field, you choose one polynomial. Then an element in the larger field K is said to be algebraic if it satisfies one of the polynomials over the field F. Otherwise, it is not algebraic, right? Next one. F of A denotes the smallest subfield of K which contains both F and A. And F of A is the subfield obtained by adjoining A to F. This is nothing but, say, already I told you F is the field and K is the larger field containing F. In between F and K, there may be many fields also, isn't it? So Among this, if you adjoin a single element A is an element from K, if you adjoin an element to F, simply you cannot add this F alone, add this A alone to F. If you add A, you have to include their A square, A cube, all the powers should be there, because then only this F of A will become what? Will become the field again. So that field, that subfield F of A, which is obtained by adjoining A to the field F, is called what? It is the smallest subfield generated by F and A. Can you understand? Right? That is, with F, we are adjoining one element and all its powers, so that this F of A will become a subfield of K. And that is the smallest subfield of K, which contains both F and A. Right? Then, next one. When will you say an element is algebraic over F? If and only if F of A is a finite extension of F. That is, by adjoining that element, you will be getting one field, no, that should be of what? Finite extension. Then only it is said to be algebraic. The next one is, an element is said to be algebraic of degree n if it satisfies a non-zero polynomial of degree n over F, but no other non-zero polynomial of lower degree. That we know, isn't it? So when will you say a polynomial is of degree n? Well, it is having the highest power as n. In the same way, an element A in K is said to be algebraic of degree n. It satisfies a non-zero polynomial of degree n, not any other polynomial of lesser degree. Okay, if A is algebraic of degree n, then degree of F of A over F is equal to n. Next one is, if AB are algebraic over F, then their sum, product, quotient are all algebraic. Okay, and also they will form a subfield. And also, if degree of A and degree of B are equal to m and n, then the degrees of A plus or minus B, AB, and the quotient A by B will not exceed m into n. Right? Next one, the extension of K is called an algebraic extension if every element of K is algebraic over F. That is, every element satisfies a polynomial over F, then the extension is said to be what? Algebraic extension. If L is an algebraic extension of K and K is an algebraic extension of F, then obviously L will become an algebraic extension of F. Okay, next let's see some problems. Root 2 and root 3 are algebraic over Q. See, root 2 and root 3 are elements in R, no? Okay, now Q is contained in R. That means R is an extension of Q. Now consider this polynomial x square minus 2 equal to 0. Then this implies what? X equal to plus or minus root 2 and x equal to plus or minus root 3. Therefore, root 2 and root 3 are what? Algebraic over Q. So how do you say like this? Actually, this root 2 and root 3 are not elements of Q, but we are saying algebraic over Q. That means these elements are taken from the extension field. The element should be taken from the extension field and they should satisfy a polynomial over Q. Then the elements are said to be algebraic over Q. Okay, the elements need not belong to the field. The element belongs to the extension field and it satisfies a polynomial over the given field Q. Right? Next one. If they are algebraic, we can find their degree, no? So, degree of Q root 2 over Q is equal to 2 because what? This is the smallest degree polynomial satisfied by root 2. And similarly, degree of Q root 3 over Q is equal to 2. In this way, you can identify. Otherwise, by definition, how do you find degree of Q root 2 over Q? That is, how do you find degree of a field over, that is extension field over a field? You have to consider the dimension of the vector space. See, this is Q root 2, no? Then 1 comma root 2 forms a basis, right? Therefore, the basis means what? Dimension of Q root 2 over Q is equal to 2. In this way also you can find out. Similarly for root 3, right? If you want to find the dimension of a vector space over the field, right? Here you take x equal to root 3, x square equal to 3. That means we find the smallest, what? Smallest non-zero polynomial which is satisfied by the given number. Okay, that degree is called what? Dimension, and that will form the basis, and from there you can find the dimension or degree of the extension field. Next one. What is the degree of q of root 2 plus root 3 over q? See, let us take x equal to root 2 plus root 3. You square it or cube it until you get only the elements of q, because we have to define a polynomial over the field q only, no. So square it or cube it, whatever thing you do, something you do, so that you get a polynomial whose coefficients are purely elements of q alone. See, first I am squaring this element, so what I am getting, x square equal to 2 plus 3 plus 2 root 6. Again, this 2 root 6 is there, this root 6 is not in q. So what I am going to do is I am trying to eliminate this root 6. So for that I rewrite this equation, x square minus 5 equal to 2 root 6. Now again you square it. So x square minus 5 the whole square equal to 4 into 6 equal to 24. Now I arrived at a polynomial equation whose coefficients are purely in q. So this is the polynomial over q which is satisfied by this root 2 plus root 3. So this is the polynomial, minimal polynomial satisfied by this. That means degree of q root 2 plus root 3 over q is equal to 4. Okay, then what will be the basis for this one? Basis means, see, for all the things you have to put one identity 1, and then this root 3, root 2 and root 3 are there, no? They put that root 2 and root 3 and look at this calculation. What are the different elements we are getting here? Root 2, root 3 and root 6. So these together constitute the basis for q root 2 comma root 3 over q. Okay, then next one, degree of q root 2 plus cubic root of 5 over q. Again the same thing, you take the element as x, square it or cube it, something you do, so that you get a polynomial whose coefficients are purely rational numbers. So first let me rewrite the term, x minus root 2 equal to cubic root of 5. Take raise the power to 3 on both sides. So x minus root 2 the whole cube equal to 5. So I am expanding this. This is like a minus b the whole cube, no? So a cube minus b cube minus 3a square b plus 3ab square equal to 5. So simplify. See, here also I am not getting purely rational coefficients. Root 2 is there. Root 2 is not a rational number, no? So I am trying to rewrite this and do something for removing this root 2. So rewrite this equation and then square on both sides. Then what I get? X cube plus 6x minus 5 the whole square equal to 2 into 2 plus 3x the whole square. Now I arrived at a polynomial equation which contains purely the coefficients from the rational numbers q. So this is the minimal polynomial satisfied by this root 2 plus cubic root of 5. So what is the degree of this polynomial? Degree of this polynomial is 6. So the degree of q of root 2 plus cubic root of 5 is equal to 6. If you want to know what will be the basis for this as a vector space over q, look at these calculations. From this you can write. See, obviously 1, root 2 and cubic root of 5 will be there. Okay, apart from that, what are all the elements will be there? See, cubic root of 5 is there, no? Cubic root of 5 is there now. Then you should have its square. So what is 5 square? 25. Cubic root of 25 should be there. Then, right, that is, if it is cubic root, you have to take power 1, power 2. Power 3 no need to take. If you take power 3, it will be cubic root of 125. It will be simply 5, which will be covered by this number. Okay, can you understand? If it is cubic root means you take cubic root of the number, cubic root of square of that number, up to that you have to write. After that no need to write. Then, so I am stopping with this. Then after that, this is also irrational and this is also irrational. No? You take the product of these two. So root 2 into cubic root of 5. Another one is root 2 into cubic root of 25. So these two products will come together. So totally how many elements? 6 elements are there. So this will constitute basis for this vector space over q. So this is how you have to find out the basis. Understand? So if you are having 4th root of 5 means you have to write 4th root of 5, 4th root of 25, 4th root of 125. Up to that you have to write. Then the next element will be 4th root of 625. That you need not write. Okay. Right. So here I have explained. If you are not confident about writing this, you do like this. Now you consider root 2 plus cubic root of 5. No, if you expand, you are getting cubic root of 25 and square root of 2 into cubic root of 5. So these two elements you have to add here. And if you cube this, what will you get? Square root of 8. Square root of 8 can be written as 2 root 2. So that will be covered by this element. So no need to take this 8. And here look at this element. Here I am having cubic root of 5 and cubic root of 25 into root 2. So these are the elements I have included here. Either you can write from here or here. Okay, whichever way you feel better, you follow that one. So I am writing, finally I am writing the basis for q of root 2 plus cubic root of 5. Then next one is q of root 2 plus cubic root of 4 over q. The same problem which we have already done. So let me take x equal to this value. Then rewrite x minus root 2 equal to cubic root of 4. So raise the power to 3 on both sides. X minus root 2 the whole cube equal to 4. So if you simplify, I am getting one more irrational number, root 2. So square on both sides. I am getting a polynomial of degree 6. So the degree of q of root 2 plus cubic root of 4 over q equal to 6. Now we can write the basis, no? So basis, how will you write? 1 root 2 cubic root of 4. Cubic root of 4 means next one what should come? Cubic root of 4 square. That's all. Then product of these two. And then product of these two. So square root of 2 into cubic root of 4. Square root of 2 into cubic root of 16. Since all are multiples of 2, I have simplified this expression further. Okay, this is 2 power 1 by 2. This is 2 power 2 by 3. This is 2 power 4 by 3. This is 2 power 1 by 2 into 2 by 3. This is 2 power 1 by 2 into 2 power 4 by 3. If you are particular about the exact basis, you proceed on to the simplification. Otherwise, you can stop here itself. Okay, then I have removed all integral powers of 2. See, 1 by 2 and 2 by 3 I kept it as it is. This 4 by 3 we can rewrite it as 2 power 1 plus 1 by 3. No, then this 2 power 1 we can remove because that will be covered here. So 2 power 1 by 3 alone it will simplify. And similarly this is 2 power 7 by 6, which I can write it as 1 plus 1 by 6. So this is simply 2 power 1 by 6. The basis element will be simply 2 power 1 by 6. And similarly here it is 2 power 11 by 6, which is 2 power 1 plus 5 by 6, which is simply 2 power 5 by 6. That is, if you want to write purely the basis elements, you proceed up to this. Otherwise, you can stop here. Okay. The next one is splitting field. If f of x is a polynomial over f of x, then a finite extension E of f is said to be splitting field if f of x can be factored as a product of linear factors over E and not over any other proper subfield. So in which field you can factorize a given polynomial into linear factors is called splitting field. Okay, if the degree of the polynomial is equal to n, then degree of the splitting field will be less than or equal to n factorial. Then one formula for finding splitting field for x power p minus 1 when p is a prime number, it is p minus 1. Okay, that is the degree of splitting field for polynomial x power p minus 1 is p minus 1. This p is a prime number. Suppose if n is greater than 1, then the degree of the splitting field x power n minus 1 will be phi of n. Phi is the Euler phi function, that is number of positive integers less than n and relatively prime to n. Let's see some problems. Determine the splitting field for the following polynomials. X cube minus 1. See, this 3 is a prime number, no? So for prime number, what is the degree of the splitting field? P minus 1. So that is 2. And x power 5 minus 1, the same thing. 5 is a prime number, so degree of the splitting field equal to 5 minus 1 equal to 4. Then next one is x power 6 minus 1. Here 6 is not a prime number, so the degree of the splitting field will be what? Phi of 6. Phi of 6 means what? That is the number of positive integers less than 6 and relatively prime to 6. So what are the positive integers less than 6 and relatively prime to 6? 1 and 5. So two numbers are there, no? So degree of the splitting field equal to 2. Now x power 8 minus 1. Here also phi of 8. Phi of 8 means number of positive integers less than 8 and relatively prime to 8. How many numbers are there? 4 numbers. 1, 3, 5, 7. So degree of the splitting field equal to 4. Next x square plus 1. This how will you write? X plus I into x minus I. Q of I will be the splitting field and degree of Q of I over Q is equal to what? 2. Okay, so the degree of the splitting field equal to 2. Next one, x cube minus 2. This how can you write? X cube minus cubic root of 2 the whole cube. So this is like a cube minus b cube, no? Which we can write it as a minus b into a square plus b square plus 2a square plus b square plus ab. Right? Now for this factor q of cubic root of 2 will be the splitting field, but for this one, this is not the splitting field. This one is having splitting field of degree 2, isn't it? Therefore, together the total splitting field will be what? 3 into 2 equal to 6. Okay, the splitting field for this one is Degree. What is a degree? 2, no? So it is 2. So 3 into 2 equal to what? 6. Okay. That's all. Thank you.